Hello? Everyone hear me? Good? Nice. What about Zoom people? Friends from Zoom, can you hear me? And also can you see the screen? Good.
Yes.
I'm wearing a mic now, and I know that sometimes you may hear echo. So I want to make sure, is the audio quality good enough from Zoom?
Yeah.
Yes. Cool. Okay, thanks. Yeah, if oh, you guys do hear a little bit echo? Just give me a second. Let me see if there is a way for me to get rid of it. What about now? Is it better? Can you hear echo now? Okay, cool. All right, thanks. Hello, everyone. Welcome back. Today we're going to continue to talk about software vulnerabilities, and we will talk about a new type of vulnerability. We talk about command line injection. We talk about path traversal, or called directory traversal last time. And today we're going to talk about a stack-based vulnerability called Stack Overflow. I suppose that you guys already know about stack, right? You know that there is a stack data structure in the operating system. So that structure turns out can be vulnerable if the program that we write, is not secure enough. So today we are going to talk about how insecure it can be, and how to find such kind of vulnerability, and also how to trigger this kind of vulnerability. Okay, so before we start to talk about the vulnerability itself, I will start with introducing to you how stack works in a function. And raise your hand if you have known this before, the stack structure, how stack works, local variables in a function. Good. I see some of you raise your hand. Great. And then Zoom people, if you also has that kind of background, let me know, because I would like to know, if other courses at ASU has already taught this before. Okay. So here, I'm just give you a example. So let's just start with the source code. Start with the left-hand side. We have a function here, right? So you don't have to know, you don't have to read this line by line for this function. I will walk you through and let you pay attention to those that are important. So this is a function, it's called check, right? And if you see from this function, so this function contains a couple of local variables, right? So we have two local variables. One is called path, and that is a chart array, right? And then the second local variable is ras, and that is in the type of integer. So we have two local variables. When the function, in this case is check, one function check is called, and when this function is executing, those are the local variables, and those local variables will be stored on stack. And besides local variable, when we call check, we need to, store those temporary information, and especially those informations that are related to the back of check, meaning that if there's a caller calls check and function check is the callee, that we need to store those caller related information so that after function check is finished, this function is going to be returned, we can know where we need to jump back to, where we need to return to, and those information will also be stored on stack. And specifically, if we look at the stack, structure, which I show on the right-hand side, this is a stack, like a brief of the stack for the memory for the program if the function check is called. And this is, let me see, this is higher address and this is lower address. So by the time that the check is called, it will first save the original RIP. Like RIP means the return or the return address. And here RIP, it means the, the pointer that points to the next instruction. So that means that if there is a caller function and a caller function calls check, then the caller functions next instruction, like after call check, the next instruction, that value will be stored here on the stack. It's called the saved RIP, because RIP means, the register stores the current instructions address, and this saved the previous RIP. So this is called saved RIP. Again, this is the return address that, after you finish executing check, it will go back to this specific instruction and continue to execute, and it will be stored on stack. And besides that, is the saved RBP. Recall that we talked about stack last time, and for each function, by the time that it executes, there is a particular stack location, like it's a scope of stack that belongs to this particular function. When you execute it, this part of a stack will belong to this specific executing function. And the scope of the stack is kind of framed by two registers. One is called RSP and the other is called RBP. So RSP is the stack pointer. It always points to the bottom of the stack, which is the lowest address of the stack. And the higher part of the frame of the stack is called RBP. Is the based pointer. So it tells you that, okay, within this scope, that is the stack frame. That is the part that belongs to check by the time that checks is running. So that's why you see that, between RBP and RSP, it stores those local variables, for stack. That's why we see that int res and the char path array is stored within this range, within RSP and RBP's range. RSP points to the lowest address and RBP points to the highest address. And of course, we need to keep this, this range, not only just for check, but also for those functions that, calls check, that the caller functions, or maybe the caller's caller, right? So if like A calls B and B calls C and B and then C calls check, then we all need to store those location, those range of those previous callers functions, because by the time that checks return, we need to go back to the previous function. We need to go back to the caller function, right? And then storing those information, we don't need to store both the bottom of the stack and the top of the stack, because the way that x86-64 works is that it's always that, when you return your current top of the stack, which is RBP, will be relevant to the previous caller's bottom stack, which I will talk about that later on. But now you just can kind of know it like by default. And because of that, we only need to store the top of the stack on the stack, which is the saved RBP. So that's why if you look at the stack now, you see that, between RBP and RSP, those are the locations that stores check related information, such as the local arguments, path, and the rest. And then above that, right, because this is RBP and this is higher address. So above IBP, which is from RBP to, those parts, that stores the saved RBP, which is the caller function's RBP's value, and saved RIP, which is the instructions to be executed in the caller function by the time that text returns. Okay, yeah. And as Dennis said, you guys may already have those information, have this knowledge if you have taken CSE 230. So yeah, this is the like basic information of how stack works in the function. But then how it works across functions, we're going to talk about this. This is, the time that we talk about callees and callers functions. Okay, so still, let's take a look at the left-hand side, the source code. There is a function called foo, and there's a function called bar, right? And function bar calls function foo. So in this case, bar is the caller function and foo is the callee function. And we have the stack here. We have low address points to high address. And let's suppose that we are at the point that we're about to execute foo. And we are, of course, in order to call foo, we need to call from bar. So by the time that function bar calls function foo, it will first, save the RIP address onto the stack. And again, save the RIP is the instruction that right after foo. So it's going to be the instruction address that starts the statement printf. Okay. And then the next it's going to do is going to be push RBP. So if you look at function foo, it's likely that it will start with push RBP, means that, that point you want to push the current RBP's value onto the stack. And remember, before we call foo, RBP is pointing to the top of the stack for function bar. And then when we call function foo, the first thing it's going to do is going to save the current RIP. So it's going to do a push RIP. So it's the put the current RIP, the next RIP onto the stack. And then it will start the function foo, and it will do push RBP. So push RBP will move to copy the value of the current RBP and save that on stack, right? So that's why you see that RSP move to lower address support, because we have a push instruction, push RBP. All right, and then the next is move RBP RSP, and it means that currently you want to move the value from RSP to RBP. So RBP in this case will be as equal as RSP. So if you check this two difference, so after we do move RBP RSP, RBP will be equal to RSP, right? So that's why RBP will also point to this location, right? Which is the location that saved RBP. All right. And then the third part is we're going to subtract our ISP by some offset. In this case, it's hex 50. So after that subtraction, RSP will start to point to the lower part of the stack. And this entire process gives us this nice, stack layout, which we have stored the previous save RIP. We stored the previous RBP for function bar. And also we construct the stack frame, that scope for the new function foo. And after that, function foo will start to execute just as what is said here, like assign the local variable, x equal to 0, y equal to 1, etc. So by the time that foo finishes, right, we need to return back to function bar. And now I'm going to show you how stack works and also how those instructions works together with the stack so that we can restore the stack frame for function bar. So the first thing it's going to do is call leave instruction, and leave is equivalent to two instructions. One is move RSP RBP, means that you move the value from RBP to RSP. By the way, this is Intel syntax. And then you pop RBP. So first is move RSP RBP. So now RSP is equal to RBP, right? So that's why it points to this location. Remember that before, the function starts to return, RSP always points to the bottom of the stack. But then because of the leave instruction, the first thing it's going to do is RSP starts to be equal to RBP. So it starts to be equal to the higher address of the stack. And then it will pop RBP, means that if you go back here, when we do pop RBP, the current saved RBP value will be popped up and then pass that to RBP, right? And also because this is a pop instruction, that's all about stack, right? Because if you're gonna do a pop and then stack's bottom address will be changed. So that's why RSP's value will also be changed. In this case, then we have RSP points to, a slightly higher address because RBP's value has been popped up, and RBP, because of the saved RBP's value, starts to point to the callers frames, like the caller space pointer. And after that, it will do return. And the return instruction it's equivalent to that you pop RSP again, and then put that value to RIP. So it's equivalent to pop RIP and then jump RIP. So you pop RSP again, that's why RPC goes to a little bit higher again. And then you give that value to RIP, which points to the next instruction. And then you jump to that instruction's location. That's how you go back to the bar and continue to execute after your call full. All right, so far so good. All right. So we have no more questions, then we can start to talk about the Stack Overflow vulnerability. So as what it says, by name, Stack Overflow means that you want to overflow part of the stack, and then because of that overflow, we can gain some unexpected privilege. So for example, here, let's take a look at the source code. We have this, check function again. And in this check function, there is a local variable called path, which is a chart array, right? So we have a character array, and that array is composed of 50 characters. So it's 50 bytes because each character represents a byte. So the vulnerability here is that when someone that, pass this ID into the function check. So the ID will be appended to function path, to argument path. Although we check, because of path traversal, we talk about we need to verify that the path is true path. It's not something that, we can trigger, some path that is outside of the scope that we want this to visit. So we have a valid path. We check the path, making sure that the path doesn't go beyond to, the locations that we want. So suppose that we have passed a valid path, and then the program will execute this cat, command, right? And in this case, we no longer have command injection because we use exccl, and there's no way for us to put two bash commands together at one command and let the program to execute. So we let this check function to execute cat followed by the path argument. And again, this path argument is composed of two parts. One is the folder called record, and the other part is the string that has been fed from the argument, coming from check. So suppose that ID is something that we can control, okay? So the problem here is that if ID, that chart array is actually longer than 50, there's no check mechanism here to check the length of the string. So if the string is long, then what could happen is that by the time that as printf is called, so ID along with this like record prefix will be all passed to argument path. And then argument path will be overflowed, right? Because we can make a very long, string that overflow argument variable path, and all the way down to the saved RIP, which is the return address. So we can change the stack save. We can change the saved RIP save. We can change the value of the saved RIP stored on stack, and then we can change it with an arbitrary value. It can be decided by argument ID. So I saw messages here says that if the programmer is smart, they fill that array with asterisk and copy. A write code for an arbitrary large string is bad. That's right. So we will talk about the defense later on. So here, because it uses as printf and there's no, like length check, that's why we can change the length of ID so that we can make this as printf, this like, string print as long as what we want, all the way down to, save the RIP. And that's why we can manipulate the control flow in the sense that by the time that function check returns, it will jump to wherever it's stored here, stored at save the RIP place. And we could do is if there's a win function, right? Or if you, in the future, if you see the assignment, you may find a win function that will just read the flag and pass the flag to you. Then you could do is just overwrite that save the RIP's value with the so-called win function. Okay, and in that case, you will call win together and you will get a flag. And again, this is all because of this vulnerability stand in as printf. All right, so that is the so-called buffer overflow. Again, the high level, this is because, there is a stack stored argument, a variable got overflowed, and you can, overflow the value. And because of the overflow, you can change the actual saved RIP on the stack. And then because of that, you can control where it jumps back to after the function returns, and you can just gain the control. All right, so I have a practice challenge here. You should be able to connect to it. And also you want to take a look at the binary as well as the source code at these links. All right, I will give you a couple of minutes to work on this. And I really hope that you can work on this by yourself. You can come up with this by yourself. And this challenge, you will not get a key, but you should be able to, the goal of this challenge is that you can log in, like I want you to like output this information, like your participation is locked. So consider this as a attendance, a participation registration process. So let me just show you this real quick. And Zoom people, give me a second and let me initiate the new Zoom, new share. All right, you should see my screen now. So you can do netcat and then connect to the server. After you connect to it, it asks you, to type your ASU right to check participation. Okay. So if you just write something random there, you say, okay, your participation is not locked. So the goal here is to make yourself log your participation. So this is what I expect you to have. Your participant is logged. So the challenge here for you is that how to make yourself logged into your participation. Okay. Try to find a way that you can log yourself into the participation. And you already have the source code. And you also have the binary already. In this URL. So this is the source code that you can take a look. I'm also going to show here. Oh, 1 second. I am requested to copy paste to put the link on the chat. All right. Just give it a shot. And meanwhile, I will connect to the server to see who make this successful. I saw there's comment from chat saying that you can enter the empty string to get it say it's locked. Well, the challenge here is not only just get it say it's locked, but also make yourself that your ASU right, like your ID is locked there. Okay. So question here, how did I run the stack file? So yes, the link give you a download, and that is exactly the binary that, if you interact with the server, the exact binary that you're executing. So you want to run that stack, that binary in a Linux operating system. As long as you're running on Linux, you should be able to run it. And it's okay that you run it. And actually, in fact, you should run it in order to, understand how that works. All right, so anyone has any clue? It's okay that you haven't solved it, but does anyone have a clue for how to solve this? No? Yes? Not really. I mean, the access function is a C's say operating system levels function that will just check if that particular path is accessible. Means that, does it exist a file? So the first thing that we need to do is to pinpoint the vulnerability, right? So instead of thinking about how to exploit, I will ask you guys to, first of all, read the source code, tell me what it does, what each function does, and then let me know where's the vulnerability. Okay. So I will give you 2 more minutes to read the source code first, and then tell me what are those functions doing. Okay, let's take a look at this together. So I see Brandon from chat from Zoom says that this this function or this program is trying to check if there is a folder with the residue right in the records directory. So it's not really the folder, it's the file, but I mean, it's similar. So what it's trying to do here is that, starting from the main function, it will first print, this, message. And it asks you to type your ASU right to check participation, right? And then it will take your string and then store that in the argument in the variable ID, and then call check ID function, right? And then if check ID function returns true, then it will say, okay, your participation is locked. Otherwise, you will see the participant is not locked, right? And then the check function, what it tries to do is to copy your ID, right? So put your ID string into the string path, and then check if path is accessible, meaning that if the file path exists or not. Okay, and then for function record, what it tries to do is that it outputs this message, ask you for your ASU right, and then check the length of the ASU right, and if everything is valid, like here it calls valid ID function, right? Which checks if the string s has contains anything that are not digit or not like a letter. If so, then it will just return 0. So it check your ID, and if your ID is valid, then it will then come up with this path, which is the the records, the folders directory, the folders path, as well as your ASU rights, the ID, that it will come up with the file, and then it will create a file under that path. So in order to make yourself log in into the participation registration system, you need to call record, basically, right? So record is the function that will interact with you and ask you for your issue right, ask you for your information so that you can put yourself into that system. Okay. Okay, so this is how the program looks like. So far, so good. Do you understand the program now? Okay, good. Okay, then the next is vulnerability. Okay, so how can we utilize this, this program to call record, to call record, given the fact that record has never been called from the main function, just like a that code here, right? You cannot really reach it. So the vulnerability here is inside function check. We just talked about the buffer overflow vulnerability. And in this case, it is the sprint f function that lacks the check, for the length of this string, because it's gonna copy paste that string to path, and path has a length of 50. But then your ID can be arbitrarily long, so that it will overflow variable path and overwrite the saved RIP. Okay. And let me just turn here, right? So it's similar to this. So we have this check, right? And because of sprintf, that's a little bit too long. So that's why we can overwrite the stack over there all the way down to the place that stores the saved RIP. And the only difference is that instead of calling the win function, we want to call the record function in this case. Okay, so now I'm going to give you a couple more minutes to see if you can come up with the tag. So how to construct the ID that you fed into, the login system, so that you can overwrite the saved RP on the stack and get to the record function. And in order to do this, I recommend you to have a Linux machine to run this binary, which I already give you the link. So run the binary and see how you can interact with the binary in order to overwrite the saved address. Question, do we need to download the binary or can we just use NC? If you want to solve this challenge, I mean, the ultimate solution doesn't need you to download the binary, but in order to understand how they work, and in order to get to the solution, you need to download the binary, and you need to run it. All right, let's work on this together. So I suppose that you already have the link, right? For those that you want to play and you want to do this by yourself, you already have those links, right? Okay, I'm gonna just hide this because I do not have enough big panel to show all the information all the time. Okay, so you should already have the stack, this binary also, if you already downloaded it. So you run it. You see that it asks you, for your tech participation, right? You can just put something over there. Actually, yeah, I'll just put some stuff over there. It says, okay, your participation is not locked. So the first thing that we want to do is let's just try to overflow it. Okay, so let's just not care about the exact address that we want to put. What is the value of the address? Let's just try to overflow it. All right. So, but then in order to overflow, actually, I still need to show the slides. Actually, let's do this. I think this is better. We need to find the address of path, right? So we need to find the address of the path, and then we need to calculate the difference from here all the way to the place that we have the saved RIP. Okay, so let's do GDB stack. now we're about to run it. And let's set a breakpoint. Set a breakpoint at this check location for now. All right. So we set a breakpoint, check, and then we run. Okay. So we just put some random string. Actually, let me just put a bunch of A's because that for that one, it's going to be easier for us to see that from our stack later on. Okay, now we are at check. Let's see. That's why we see that argument ID has the value of A that repeated for 15 times. Okay. So now let's take a look at the stack. What you could do is you could have, actually, let me just still execute something more. Okay. And then let's do InfoFrame. And this instruction will give you the information about the current, saved registers value and the location that those values are saved. So it tells you that, okay, this is your current RIP. Okay. So it means that this is your current instructions address. And your saved RIP is equal to this value. And this is something that you want to pay attention because this is the value that you will overwrite in the future. And then they also tell you the saved registers, where are they on the stack? So RBP is at this place. And then RIP is at this place. All right. And in fact, let's just take a look at this place, RIP's place. Okay. So you could do X. We talked about those like instructions about GDB before, when we talk about reverse engineering. All right. So let's take a look at the value. I am tweaking the format so that we can see them more clear. So this is address, right? For what it says here, says that the RIP is stored at this particular address. And indeed, if you look at the value that's stored in this address, it's equal to 400,886. That's the saved RIP value, right? So indeed, this particular address stores the saved RIP. Okay. And then let's see where the path is. Where is the address of path? In order to do that, let's check, this instruction. Let's check the instruction that calls as_printf. And because we know that path is the first argument, right? And we know that according to the 664 calling convention, the first, argument will be stored as, register RSI. So we can take a look at the current register value when as_printf is about to call. But then we need to know where as_printf is about to call. So what we're going to do is let's quit this. All right, I'm going to use tmux. Let's find the instruction that calls as_printf. And we know that's inside function check, right? Let's find call as_printf, which is here. Okay. So let's use GDB to execute into this place and then check the value of RDI, which stores the first argument. All right. Again, GDB stack. Set a breakpoint. And this time we're going to set a breakpoint here. Okay, let's run. Some random string over there, which I don't really care. And now we are at 400,9F6. That's the place that I'm about to call sprint F, as_printf, right? And this is the command that we talked about last time when we talked about reverse engineering, right? We can use X \I $PC to check the current instructions that to be executed. Okay. So let's take a look at the argument then. So let's print the value of RDI. So it gives us this argument. So this should be the place that is going to store the, this is the place that's going to be stored the, the path, and this is the address of path. And in fact, let's just continue to execute it. So let's do a next I. All right. So let's take a look at this address. Okay. So it indeed, let's put this, right? So we see that those are the strings that are stored at this place. So this is the start address of path. And again, let's use InfoFrame to check the current address that, saves the saved RIP. It's at this particular address, right? Okay, so now we know that this, here is the path, right? The start of the path, and this is the location that stores the saved RIP. All we want to do is to overflow this all the way down to here, right? All the way down to here so that we can overwrite the saved RIP value. And indeed, if we check the RIP's value here, it's equal to this value. Okay, so now I'm going to give you a couple more minutes to work on this. So now you know that your goal is to, write some value from here all the way down to this location. And you can calculate the length of the string so that you can trigger, memory corruption. You can change the value. Okay, so you have calculators. You can calculate this by yourself. So calculate the difference between these two first, and then subtract that with this prefix record slash, and you should be able to calculate the actual length of string that you want to put into this challenge. And let me know after you calculate it. All right, can anyone tell me how many bytes that you need to write? So in order to overwrite the saved RIP, we know that the string will start from here. Well, the string will actually start from here, but the ID that you're going to put will be starting from this place. And then we need to use that all the way, make this ID's length very long as it will overwrite the saved RIP, which is at this particular location, right? So then how long is the string in order to have us to reach this place? We need to have this subtracted by this, right? Okay, and what's the value of it? Can someone tell me? No? Okay, let's work on this together. Open Python 3 or whatever calculator that you like. Put this value here, right? And I have that subtract by this value. That's 64. Okay. So that means that if you are going to write 64 bytes, then you'll be able to reach this address and have a chance to overwrite this place. Okay. Okay, so now to justify that this works, let's do this following. Let's start to write a, a string that contains 64 more bytes. Okay. That is 4. Okay, that's 8. Okay, so that's 16. Okay, this should be, this is 64 bytes. Okay, and let me just put something more there. So it's BBBB. All right, so let's make this as an input. And let's just have this program run using this input. Start. Okay. So this is the place that we're about to call as printf, right? Let's take a look at the InfoFrame. So currently the saved RIP is this value. Okay, now let's continue. Run a little couple more instruction and check the frame again. It changed. And now, in fact, let's continue to execute it. You will receive a segmentation fault. And the reason for that is because the program considered this as the instructions that it wants to execute after, the check function returns. But apparently, this is nothing that you can refer. So that's why it triggers segmentation fault. It cannot access this particular location to get to the next instruction. All right. Okay. So now you have a way to overwrite the saved RIP. And now the question is, then what exactly the value that we want to put there in order to overwrite the RIP to something that we are interested in? And what are we interested in? We're interested in the function called, actually I forgot the name. Let me say it again. No, it's called record. So we want the saved RIP points to function record, right? Okay, then where is function record? Let's take a look. You can use opt-down disassembly to get it, or you could just use -t, which you will be able to get the function symbols from your binary. And let's grab record. Okay, here we go. This is the function's address. Okay, so that's 400,874. And this means that instead of changing the value to this, like BBBB, let's change that to this particular value. How to do that? I'm gonna write this somewhere because I've had a bad memory. Okay. You know what? Let me just, this is too small. Let me just copy paste here and create a new session. All right. So let's go back to the input. We know that this, first 64 bytes are used to just overwrite everything into the saved RIP address. And starting from there are the actual places that you are going to overwrite the saved RIP. So that means that we need to replace this part with the value that we just talked about, right? Which is this. And remember, this program is little endian, right? So for little endian program, that means that for this particular byte, which part goes the first? it's this byte goes the first, right? Byte 74 goes the first. So that means that what we really want to have is, hold on. I'm moving my cursor. Okay. So here should be the byte of 74, right? And then followed by that is 08. And then followed by that is 40. We want to change that in this way. And of course, we cannot just do this and save, because in this case, then it will consider like backslash as a character, X as a character. We need to make it as a byte. Okay. So now we can write a very small, short Python script in order to, write this into the file. And let's do this. All right. And you can also just use struct. Remember that we talk about struct, struct.pack, right? We talk about that function before when we do talk about a little or big ending. In this case, because we don't have too much byte, I'm not gonna use it. I'm gonna just directly manually change that. So what we need to do have, the attack string, call it attack, is equal to some random character. Doesn't have to be A. I mean, I just tend to use A all the time. And then times 64 bytes. And then put 74, 08, 40. All right. You can make it as a byte. And then input. All right, so it's very easy. You just write this entire thing into the file, and you should be able to just run it. All right, so we already have the attack input. Let's see if it works. So we run stack again with that attack input. Okay, somehow it gives you a segmentation fault. Let's take a look at use GDB, go back and see what happens. So now let's do run with attack input. All right, so this is a place that we are about to, call as per f. After that, let's take a look. Okay, so there's something wrong with my current story. Say the RP is equal to this value, which is not exactly that we want, right? We want it to equal to this value. But here is 874 instead of 40 and then 0874. Looks like there's something wrong with my first bytes. Let's take a look at it. Let's take a look at our attack input. All right. We do have 40. Then let's take a look at argument ID, because ID is where we store those. Okay, so you see that for some reason, we didn't manage to pass the bytes over here. Yes. The last character got 0 out. Right. So let's take a look at the intact. We need to make a dash in there probably. Okay, let's take a look at that input again. Okay, finger crossed, hopefully this works. Let's run that again. Here we go. Now we got it. Okay, so now let's continue to execute it. You see that it starts to ask you what's your ASU right. So function record got executed. Now we just need to feed into your ASU right ID. All right, so let's go back. We know that after this line, we'll go to the right place, right? So that means that after that, let's put our USU right. I'm gonna just put attacker here. Okay, and it should work. Let's do this again. Continue, runs from the beginning, but then we don't need to. All right. Although it's still called segmentation fault. It should already work. So now we have this attack input. Next, what we could do is we could do netcat. And then the place, the address. Let me find the address. Right? And then feed that into attack input. Okay. And now let's netcat this again. Check our participation. Now your participant is locked. Okay. So we managed to overflow this service and put our participation over there. In your future assignment, you will be also asked to do something similar to this. You know, try to find the vulnerability and overflow it, and then call the so-called winning function, and then in the end, get the flag. All right. So any questions here? I see someone asking from Zoom to let me to show the Python script again. Sure, I'm going to show that. So there are comments here saying that interacting with the using Pong tools might be easier. Yes and no. It's just because this challenge is particularly easy. There's no much that you need to interact with. So you don't really need to use Pong tools in this case, because like there's only one-time interaction. You just need to send a string there right away instead of like receiving information and extract information. But you will be expected to use Pong tool to interact with the challenges, you know, for challenges in the assignment, and then use that to extract some information like the B piece, like the base pointers information or stack pointers information in order to do your attack. Okay, I also see some of you guys say that you also hit a segmentation fault. It's normal because but you need to like look into why there's a segmentation fault. In this specific case, this is because by the time that you overwrite it, the time that you have the main function, you overwrite it, and then by the time it returns, it will not be able to recognize the overwritten value. So that's why it triggers a segmentation fault. But you already finished your participant recording anyway. So that's why, it's okay that you just quit it, and then you will still be able to get the your participation. Okay, someone asking me to show the attack input. Right, okay, cool. So this is the attack input. And it may be better if you just show the bytes here. So the first 64 bytes are all just A, just like the buffers that you want to overflow. And then starting from, the 64th byte is the return address that you want to overwrite. And then followed by that is, your ASU write ID. And also Justin has shown the, let me just put that here. I think this is also a nice way. All right, you also use this. So if you have Pong tools, then you can just have, use the function called P64 that will convert this byte directly to little endianness 64 bytes. And you can have that, the buffer, and then plus. All right. So for those that you still don't understand this, I highly recommend to go through, because this is going to be recorded, to go through this video and really just write this challenge by yourself. I think that is a very important thing. By the time that you make yourself hands-on, you will understand this much more. And again, the high level idea is that you find where the path is, find the path's address, and then you find where the saved RIP is, which you can just get it by InfoFrame. And then you overwrite starting from the path argument all the way to the saved RIP so that you can overwrite that value to something that are interesting. And in this case is the function called record. All right, we are running out of time. That's pretty much for today. And thank you everyone for coming.